So we've got some more work problems here. How much work is done lifting a 10-meter chain over the side of a building if the chain has mass density of 5 kilograms per meter, and we assume gravitational force here, that pull is 9.8 meters per second squared. Okay, so let's draw a picture, kind of understand what's going on here. So we've got a building, and so some guys on top of this building, and they're pulling up a chain. And it's 10 meters long. Okay. So how much work is done lifting a 10-meter chain over the side of a building if the chain has this mass here? So the mass is equal to 5 kilograms per meter. All right, so since it's 10 meters, the whole chain's 50 kilograms, sorry. And what do we have going on here? How are we going to figure out this work? Well, what I'm going to do is I'm going to take an arbitrary piece of the chain, so some arbitrary piece of this chain, and I'm going to call it delta y, some delta y slice, okay, right? It's a change in the y value, so y1 to y2, so it's changing as I'm pulling it up, right? Okay, and then I know this whole chain is 10 meters long, okay, and I want to say the distance from where the guy's pulling it up to some arbitrary little segment of the chain, I'm going to call that distance yi meters, okay? So this is the distance in meters from the top of the building, okay? So that yi is how far away we are from the top of the building at any given point there, right? So my work for one arbitrary little segment of the chain, to pull this little segment of the chain up to the person, that work done is approximately, well, the mass, 5 kilograms per meter, multiplied by the change in y, that little segment of the chain, or the chain, multiplied by the gravity, 9.8 meters per second squared, and then multiplied by the distance yi meters, okay? And then that work, remember that work here, Newton meters measured in joules. So what is this reduced to? This is going to be 5 times 9.8 times yi delta y joules. Okay, so that's for one little segment of the chain right there. So some arbitrary segment of the chain. So the work needed to lift this segment of the chain to the top of the building is this piece right here. Okay, so now I'm going to sum all of those little delta y segments, and then of the chain from 0 feet from the top all the way to 10 feet from the top. So I'm summing all of those up. So to do that, I need an infinite sum. So the work is equal to the integral from 0 to 10, okay? Sum from 0 feet away to 10 feet away, okay? All the little segments, 5 times 9.8 y dy, okay? When I integrate this here, I get 24.5 y squared from 0 to 10, which is equal to 24.5 times 10 squared minus 24.5 times 0 squared gets me 2450 joules. So 2450 joules of work is required to lift the chain, the 10-meter chain, over the side of the building, lift it up there, okay? Now you think about it as you're lifting that chain up, what's happening? Well, once you pull that chain up and all you have is this chain left, then that amount of chain that was left takes less work to pull up than pulling up all of the chain together. Okay, so as you're pulling up your chain, the amount of work is fluctuating. Okay, the amount of work required is decreasing the more chain that you pull in. Okay, so a lot more work is being outputted here on the first amount of chain you're pulling in versus at the end. All right, so let's try another one. Okay, so we've got a 12-foot chain with mass density of 3 pounds per foot. Okay, so 3 pounds per foot, 12-foot chain. So I guess in total that would be 36 pounds, right, for the whole chain, right? Okay, we don't really care too much about that, but just, just for funsies, we got that. This is initially cold on the ground, all right? So we've got this chain, this 12-foot chain, and it's just sitting on the ground. Okay, it's piled up on the ground there. And what we want to do is we want to take this chain and we want to lift the chain so that it's fully extended in the air, but one end is touching the ground. Okay, so what does that mean? That means, so somehow we lifted that chain up, right? That means that we lifted it up 12 feet. All right, so we went from 0 feet up to 12 feet. So we took that chain and we pulled it up, we lifted it up. Okay. So what do I need to do to figure out the weight here? Well, the mass density, okay, the mass density is equal to 3 pounds per foot. Okay, 3 pounds per foot. And let's take an arbitrary piece. So just some delta y slice here. Delta y slice. Okay. And what are we doing? We're lifting it up, right? So we're pulling it up off the ground. So I'm going to let this distance here represent yi, which is the distance in feet off the ground. So the work is pulling it off the ground here. So I'm lifting it up off the ground, okay, instead of it already being in the air like we were doing for that problem there. We're lifting it off the ground here. And an arbitrary slice of work here, so a WI. Well, what is the work? It's the mass, the 3 pounds per foot, multiplied by, well, for one chain link, okay, so one little chain segment, so a segment of the chain, delta Y, feet, and then multiplied by the distance that we move it, that delta Y chain segment, YI, feet. What does this reduce to? Well, it reduces to 3 YI delta y foot-pounds. Okay? So now what am I going to do? Well, the work needed to extend this chain fully is represented by this right here, okay, for each arbitrary segment. So in order to find the total work, I need to integrate from the segments from 0 up to 12 feet above the ground, okay? So what is this equal to? It's the integral from 0 to 12 of 3y dy, which is equal to y squared over 2 times 3, evaluated from 0 to 12. So that is 3 over 2 times 12 squared minus 3 over 2 times 0 squared, which is 216 foot-pounds. Okay, so 216 foot-pounds right there, required. All right, now you notice here we're not in joules, Newton meters, because our units here are in feet and pounds. Okay, so we stick with our units, or what's important to note, how you're doing the problem. Let's try one more where we have feet pounds. So I've got a 2,000 pound wrecking ball. Okay, so I've got this big old wrecking ball here sitting on the ground. Okay, and I've got this crane. Oh my gosh, I'll do the best I can to draw this crane. Whatever. Okay. Then we got a little guy sitting up here. A little part of this. Oh, look, he's happy, moving, operating his little crane thing. Okay. All right, so we got our little crane thing going on here. The ball is 2,000 pounds. Okay, so the ball's 2,000 pounds, and it hangs from a 40-foot cable. So the cable is 40 feet long. The density of the cable attached to the crane is mass density equal to 8 pounds per foot. All right, calculate the work done if the crane lifts the ball from ground level to 40 feet in the air. So what's happening here? So I'm going to redraw this scenario here. Okay, so I'm taking this ball and I'm going to lift it, the ball, up to right here. So I'm literally pulling in the chain, right? So that distance that I moved, the wrecking ball travels is 40 feet. Okay, so I'm drawing in. So I've got some. I want to calculate the work done that it takes to lift the ball 40 feet in the air by drawing in that cable. So there's two parts that are being done here. All right. So part one is the ball itself is being lifted up into the air, right? Well, the wrecking ball is 2,000 pounds. Okay? It's 2,000 pounds. Well, what do I know about work for for the wrecking ball? Work. Well, it's equal to what? The wrecking ball work is equal to the force multiplied by the distance, okay? Well, that force is the 2,000 pounds, okay? And how far am I moving the wrecking ball? Well, I'm moving it up a distance of 40. That weight of the ball isn't changing over time, so that force is staying constant, so I multiply F times D to get my work, okay? So what does this equal? This gets me 80,000 foot-pounds. All right, so 80,000 foot-pounds just to move this wrecking ball. Now, the other part of the scenario we got to think about is kind of what we've been dealing with in the first couple of problems. It's lifting this chain. As I lift the chain, it takes more work to lift this whole chain than whenever I've only got half the chain left there, right? That amount of chain, it weighs less. It's a weight overall is less than what it was whenever it was extended out 40. So the work required to pull in the chain is less and less as the ball goes up. So that's actually variable. That's where the calculus comes into play. So part 2 is the work required to lift the 40-foot cable. Okay, so the work required to lift the 40-foot cable, well, let's take one little arbitrary slice of the cable. Okay, so if I take one little slice of the cable, that's going to be a delta y. And how far I am away, so yi here, this is the distance the cable must be lifted. Okay, the work done. Okay, that mass, the density there, multiplied by the distance traveled. Okay, so the force times the distance. For an arbitrary work slice is equal to, well, how much is it for each one? It's 8 pounds per foot. So 8 pounds per foot multiplied by what? By the delta y slice in feet multiplied by the distance the cable is lifted, yi, in feet. And so what does this get me? This gets me 8 yi delta y foot-pounds. All right? And this represents the work needed to extend, or to pull the chain up for some arbitrary delta y slice there. Okay. Now, I want to lift all of these from 40 feet up to 0 feet, right? So all of that from 0 to 40 of 8y dy. Integrate 8y, get y squared over 2. So 8 divided by 2 gives me 4 from 0 to 40. And so this is 4 times 40 squared minus 4 times 0 squared. And so that's going to be 6,400 foot-pounds. Is that my total answer? No. What do I know? Not only does it take work to lift the chain, but it takes work to lift the ball, right? So the old ball and chain, add those two things together, 80,000 plus 6,400, and I get 86,400 foot-pounds. It's the total amount of work required to lift the ball from the ground to 40 feet in the air while drawing in the cable. Okay? So hopefully this gives you a better idea on how to work your homework problems.